Hello, and welcome to my next video for Calculus BC, section 8.3. It has to do with relative rates of growth. So we'll launch right into this here. See that when we speak of relative rates of growth, we're comparing two functions and identifying if one has a faster, slower, or the same rate of growth as x approaches infinity. All right, it ends up being a really simple test. You can see that f grows faster than g, and which of course means g slower than f, as x approaches infinity if the limit of the quotient of f of x over g of x equals infinity, or g of x over f of x equals 0. And that should make sense because the function that's growing faster will win out in the war to see which one grows faster. So if the numerator grows faster, you're heading towards infinity. All right, so let's take a look at the next piece. Meanwhile, you can tell if they're growing at the same rate if that limit is equal to a non-zero constant. So again, you take the limit of the quotient, and if it's equal to L, where L is a non-zero constant, and it's finite, so you can't have it approaching infinity, and you can't have it approaching 0. If it's approaching some other number, then they're growing at the same rate. All right, let's take a look at an example then of how to use these. So we're going to compare the rate of growth of y equals 2x to y equals x. And so you can see that we'll start off by taking the limit as x approaches infinity of, let's put the 2x on top and the x on the bottom. Okay, well that's a really simple limit. We can see that that's approaching 2. Okay, and that is a finite constant. So as we just saw from the rules before, that means y equals 2x and y equals x grow at the same rate. Now that could be somewhat unexpected, but really they're growing at the same rate. It's just that the y equals 2x is always twice as large as y equals x, yet they're still growing at the same rate. All right, so let's move on to the next example. Go to example 2. And we want to compare the growth rates of e to the x and x squared. Again, we just take the limit as x approaches 0, infinity rather, let's put e to the x on the top and x squared on the bottom. Now, it should be really easy to understand because this is an exponential function and this is just a quadratic, and of course exponential functions always grow at a faster rate eventually than a quadratic or other types of functions. But anyway, if we take this limit, we're going to find out that, well, first of all, we're saying that this is infinity over infinity. And so we'd use L'Hopital's rule. That's the reason we learned that earlier in this section, or in this chapter. So take L'Hopital's rule, we get e to the x over 2x. And that is also heading towards infinity over infinity. I said use L'Hopital's rule to get this, but of course L'Hopital's rule says we can take the derivative of the numerator and the derivative of the denominator and take the limit of that result, and you'll get the same answer. So it looks like we use L'Hopital's rule again because we're heading towards infinity over infinity. So the limit as x approaches infinity, the derivative of e to the x is still e to the x, and the derivative of 2x is 2. And that, we can see, is heading to infinity over 2, which is heading towards infinity. So y equals e to the x grows faster than y equals x squared. And that's the answer to that one. All right, I think I just have one more example here. I actually have two more examples. Okay, so we'll go example 3. Let's compare the growth rate of y equals x to y equals x plus cosine of x. Okay, so again, we'll take our limit have to make sure we're on the right section here. So example 3, and you're going to take the limit as x approaches infinity of, let's put the messier one on top, x plus cosine of x over x. Well, I think even before I use L'Hopital's rule for this, I'm going to change that to the limit as x approaches infinity. I'll just distribute the division to 1 plus cosine x over x. Okay, and we can see that the limit of this part is 1. And the limit of this, you can see that cosine of infinity, well, basically it's alternating between -1 and +1 and all the numbers in between. So the largest and smallest it ever gets is between -1 and 1. However, the denominator is getting larger and larger and larger, so that piece is heading towards 0. So often the way I like to denote that is say that like this part, do a little arrow, saying that's heading towards 0. And we end up seeing that this is heading towards 1. So we can see that this is a finite constant, finite non-zero. So go back to our other color here. Our answer is that y equals x and y equals x plus cosine of x grow at the same rate. All right. Another example here, example 4. I'm going to show that log base 2 of x and log base 3 of x grow at the same rate. So launch into the same idea, take the limit of, oops, let's undo that, log base 2 of x over log base 3 of x. It doesn't really matter which we put on top, and we're taking the limit as x approaches infinity of this. Well, who really likes working in other bases? So let's use the change of base rule, and we can change this to the limit as x approaches infinity of, so this is in the numerator, so that is ln of x over ln of 2 over, and this is ln of x over ln of 3. I wrote the wrong thing. Ln of x over ln of 3. Okay, so that seems somewhat confusing written that way. I like to go ahead and just rewrite it as a product. So it's this piece divided by that piece. So that means it's going to be the top times the reciprocal of the bottom. So we'll change that to ln of x over ln of 2 times ln of 3 over ln of x. I think that's the easiest way to really understand what's going on here. You can see the ln of x's actually cancel out. They divide out to be 1. And so then this ends up being the limit as x approaches infinity of ln of 3 over ln of 2, which is equal to ln of 3 over ln of 2. I actually did an extra step that I didn't have to do there, but that's okay. So you can see that ln of 3 over ln of 2 would indeed be a non-zero finite constant. So log base 2 of x and log base 3 of x grow at the same rate. All right, and that's, well, of course, we knew that was our answer, but there's all the work to back it up. So there you go. That's section 8.3. Hopefully you find that this one's a fairly simple one. Thank you so much for listening, and you can catch me on the next video.